Hello, everybody. This is Professor Monty. We're going into section 4.2 today, which is antiderivatives as areas. So remember we talked last time, antiderivatives are just going backwards from the derivative. So we've got the rate of change, but we want to know the original function. So consider this. Suppose we know sales are $6 per unit. And we want to find total sales for 100 units. Well, we already know how to do that because we know that revenue is price times quantity. And then if we go from there, we can say, okay, revenue R is price, my $6 per unit times 100 units. And that's going to be $600 total revenue. Nothing new there. That's stuff we already knew. But here's what is a little bit new. Consider this sales here as $6 price per unit. What that actually is, that's the rate of change of our revenue. That's actually the derivative. This is actually R prime of X is equal to 6. That's how our revenue's changing. If I sell one more unit, I'll have $6 more revenue. Well, let's go ahead and graph that, see what that graph looks like. So if I go to graph that, so here's going to be my graph. This will be number of units down here. This will be dollars. Well, if I've got a 6 right here, and I've got 100 units right here, and I draw this graph out, notice what this graph is. That's $6. That's my derivative of revenue. That's R prime of X. And then if I just go to where I have 100 units, and I find this area right down here, notice that area, let's move this up a little bit. The area, that's just a rectangle. So remember, that's just length times width. Or if you want to say base times height, it kind of looks more reasonable that way. But my area is my length, which is 100, times my width, that is 6. And it doesn't matter if you're thinking, wait, the length was 6 and the width was 100. Okay, it's multiplication. It's commutative property. It doesn't matter. But when I multiply that together, I get an area of 600. That area actually represents total revenue. That's the same 600 I got right there. These are both the same thing. And so if you notice what's happening, the area under the derivative function is the parent function, the original function. So let's state that. Area under curve of derivative, in this case, we had R prime, is the total change in the original function. Or in this case, that would have been the revenue function. Well, so what we're going to do is we're going to use this idea. This is what this whole section's about, is we're going to say, hey, if I can find the total area under the curve of the derivative, I'll get the total change in the original function. So notice, I don't know what the revenue function is. It'd be easy to figure out if it's $6 per unit, it's just 6x, but I didn't use that revenue equals 6x to find this answer. I found it just by finding the area under the curve. Okay, So let's move on from there. Let's see how this works. Let's do an application using that. So what I'm going to do is I'm going to move this up here, and I'm going to go in and I'm going to pull a problem out of the book that's an application of this. So let's see. Let me go back here. I will find my file. Here's my file. We're going to start with problem 30 in this section. And let's go back. We'll paste it in right here. And we'll answer the question. Okay. So let's go ahead and read that, figure out what's going on. So if we think about it, it says total cost from marginal cost. Redline Roasting has found that the marginal cost in dollars per pound is C prime of X, and then they give it to us negative 0.012X plus 650 if X is less than or equal to 300. So they're saying that X less than or equal to 300, they're just saying the marginal function, we don't know if it still holds past X equals 300, where X is the number of pounds of coffee roasted. Find the total cost of roasting 200 pounds of coffee. And notice, if we had the cost function, we could plug in the 200 and just figure it out. We don't have the cost function. All we have is the marginal cost function. So we will learn in later sections, hey, how do we go backwards from marginal cost to total cost to actually do this? Well, let's talk about it. I'll even give you some notation for it. We've actually seen it. We just haven't been explicitly told that's what it is yet. But here's what we're going to do. We're going to draw the picture. We're going to find the area under the curve. All right, so let's draw this picture. We've got, now notice that's just a linear function. It's just x to the first power. So that's sort of in the form y equals mx plus b. We don't see those letters because it's different letters, but it's a linear function. This graph is a line. What I'm going to do is I want 2 points on the line, because any 2 points can determine a line. Well, it says find the total cost of roasting 200 pounds of coffee. So what I'm going to do, let's see, we'll graph it out there. So I'll do it right here. What I'm going to do is I'm going to put in an X value for pounds of coffee, and then we'll find what C prime of X is. And I'm just plugging this into my calculator. Okay, so let's do, we just need 2 points. Well, I'm trying to find the total cost to go from 0 to 200 pounds. So I'll pick 0 and 200 as my two X values. 0 is easy. When I plug in C prime of 0, I just plug it in. I get 0.012 times 0 plus 650. So of course, that's just 650. So my marginal cost is 650 originally at 0 units. I'm going to plug in 200. I'm just going to do that into my own calculator. You guys have faith that you guys know how to do this, so I'm not going to show you on the calculator and use that time. But so I'm plugging in negative 0.012 times 200 and then plus 650, and I get 4.1. We'll go to 2 decimal places just because the other one is. Okay, so now what I'm going to do is I'm just going to go plot these points on the curve, and then we need to find the area under the curve. So let me erase this to get it out of the way to make sure that's not messing up our picture. And so let's do this. So here's going to be our picture. And we've got, let's see. The units aren't really that critical. Here's going to be 650, and here's 410. And we're going from 0 out to 200 units. So again, units are along the horizontal, and on the vertical, we're going to put cost, and this is actually cost per pound. We'll put LB for pounds. Okay, now at 0, let's do this in another color. So we use the blue. At 0, we were at 650. At 200, we were at 410. And so then now if we draw a line there, we'll just draw a line between those two. And then what we're doing, I didn't really go all the way to 200, did I? Make it go out a little bit more. And so there, and that's kind of not great. We'll clean that up a little bit because I can't help myself. All right, that's a little bit better. And now what we're trying to do is we're trying to find this area. I'll shade the area that we're trying to find, which you could probably tell what we're trying to find anyway, but that's the area we're trying to find. Now, the shape of that is actually a trapezoid. If you know the formula to find the area of a trapezoid, you're welcome to use it. It's not a hard formula, but most of my students don't remember it. But what they do remember is they remember the formula to find the area of a rectangle, and we have a rectangle right here on the bottom. Didn't line that up perfectly, but there's my rectangle, and above it's a triangle. So we've got a rectangle here, and if you remember, the area for the rectangle is length times width, and here we have a triangle, and the area of a triangle is 1/2 base times height. So we're going to use those two formulas. We're just going to add those two areas up. That's going to give me my total area. So my total cost, which is equal to total area, all right, let's move this up a little bit so I quit pulling that stuff down. So I'm just going to find the total area. Remember this curve up here originally, let's change pins. This curve here, that straight line is marginal cost. This was C prime of X. And so as we said before, the area under C prime is, well, let's rephrase that. The area under marginal cost is total cost. And so we're finding that. So we're just going through, we're just going to do a little bit of geometry actually here. Okay, so we've got our total area. So it's the, we'll say it's the triangle plus the rectangle. All right, so the triangle, 1/2, well, the base of that is this length of 200. That's the base of the triangle. So this up here is the same 200 as the bottom was. So it's 1/2 times 200. We'll put these in parentheses instead of putting an X there so you don't think it's a variable. So it's 1/2 the base times the height. Well, the height is just this piece right here. That's the height of the triangle. Well, that's 650 or 6.5 minus 410. That was the height. So this was the base, this was the height. And then plus the area of the rectangle. Well, the rectangle is length times width or base times height. It's still 200. This dimension down on the bottom, here was my, that was my length, if we're talking about it this way. And then this would be the width. Well, so the width or the height, if you want to, is the 410. And now I'm just going to do this on my calculator. I'll do it as two pieces. So let's see. I've got 1/2. Well, 1/2 of 200 is just 100. I'm just going to say 100 times, and then in parentheses, I'll let it do the math for me. 6.5 minus 4.1. I guess I could have done that in my head. But this piece is 240. Plus this piece, well, we can just kind of do that in our head, can't we? That's going to be 820. And then if we add them together, we get 1,060. And that is my total cost. Total cost. And that was for producing 200 pounds of coffee. Should I say pounds? Should I write it out so I don't confuse anybody? Pounds of coffee. All right. Hopefully that made sense. What we're going to do is we're going to do another one. We're just finding the area. So sometimes areas are fairly easy to find. Sometimes it's just a triangle. Sometimes it's just a rectangle. You only have to do one piece. But in a case like this, we just broke it up into two pieces and then added the two areas together. Okay, so there's a good start to us. And that's good geometrically if we know how to find the area. Here's what I mean by that. Let's look at another example. So what I'm going to put up here is, let's just do this one. It's just an example. This isn't one out of the book, but it says, suppose, now what I have, because remember, I'm trying to find the area of the curve. So this time, the curve that I'm looking at is f of x equals x squared plus 1. Now it's not linear, it's not a line, because that x squared makes it a parabola. So suppose f of x equals x squared plus 1. I'm going to say, I'm not going to say anything yet. Let's erase that piece. Let's look at the curve. So if I look at this curve, let's say, if you remember the x squared is a parabola, it opens up because it's positive. The plus 1 says move the whole thing up 1. So the curve looks something like this. It's going to go through 1. I probably shouldn't put a dot there yet, but it looks something like this. Well, that's not so bad. And I've just highlighted the first quadrant over there. So here's x, here's y. But the graph looks something like that. So that's the graph of f of x equals x squared plus 1. Here's the problem. What I want to do is I want area under curve between, oh, I shouldn't have written between there. I didn't have enough room. Between 0 and 6. The problem is that's not a line. If I do that area and I go out to 6, and I'm going to have a small scale on my x so that I can fit everything in. So let's say this is 1, 2, 3, 4, 5, 6. If I want this area under that curve, that's not a line. That's not a triangle. I can get a rectangle on the bottom, but that's still not a triangle on the top because that's a curve, not a straight line. So at this point, if I want to do this geometrically, the best I can do is that I can approximate how much that area is. So what we're going to do in this problem, we're going to approximate area under the curve between 0 and 6 using 3 rectangles and left-hand endpoints, whatever in the heck that means. Let me draw what I'm talking about. So here's what I'm going to do. I need 3 rectangles. So one rectangle is going to stop here. One rectangle is going to stop here. And the other one's going to stop here. So it starts here and it ends here. I'm using the left-hand endpoint. So I'm going to go up on the left-hand side till I hit the curve. And then I'm just going to make it a rectangle. Notice I don't get all the area. The second one, I'm going to do the same thing. I'm going to go up till I hit the curve on the left-hand side, go over, and have another rectangle. And then I do the same thing for the third one. I go up till I hit the curve, make a rectangle there, because I can find rectangles. And so what I'm doing is I'm going to find the area of those 3 rectangles. And the problem is, obviously, that's not all the area because I've got these gaps in there. but it's going to approximate it, and then I'll tell you what we would do from there. Now, I'll tell you what this really is. We'll talk about that later. We don't even need to talk about what it really is yet. You're going to learn next section. Okay. So we're going to approximate those areas, but we need to use those three rectangles. So here's what we do. In order to find this height, so remember we're doing length times width? Well, let's see. This was 0, 1. I don't want to number those. Let's not number those. But we do know it goes all the way up to 6. Yeah, I changed my mind again. We'll number those. 0, 1, 2, 3, 4, 5, 6. Now, let's just take one of those rectangles. Let's take that first rectangle. We'll take this rectangle right here. I want to find that area. Well, it's a rectangle, so we know my total area is going to be rectangle 1 plus rectangle 2 plus rectangle 3. And each of these is just length times width, length times width, length times width. Now the length, if we're talking about this being the length and this being the width, the length, notice they all have the same length. Let's put that up here. The length is just how far we go in the x direction. So we're going to call that delta x to mean the change in x. But that change in x is my total change divided by how many rectangles I have. So that's total divided by number of rectangles. Well, notice that total was 6 because we went from 0 to 6. And the number of rectangles were 3. So my delta x, they each have a width of 2. We call that the length. So that's my length of each of those is going to be 2. So I know right away when I do the area, I say, oh, it's 2 times something plus 2 times something plus 2 times something. Because these all, and we can look, I go from 0 to 2, of course, that's a length of 2. And I go from 2 to 4, again, a length of 2, and then 4 to 6. I just need to figure out what those widths are. Well, the width is determined by whatever that point is on the rectangle that I drew up, where it hits the curve. The formula for that was f of x equals x squared plus 1. So this first one is actually going to be whatever I get for f of 0, because I plugged in 0 to determine the height. So this is actually going to be f of 0. The next one, the height was determined at x equals 2. So this is going to be f of 2. And then the last one will be f of 4. Notice 6 didn't determine the height of the rectangle, but the side 4 did. And that's because we're using left-hand endpoints to determine those. So I just need to find out what those are. So I'm going to do a little one of these again over here. You don't have to do it that way, but to show you what's going on. So I'm going to go x and then f of x using the formula x squared plus 1. That's what f of x was. So I'm going to plug in the x values of 0, 2, and 4 into that formula. So I'm plugging, notice what I'm doing is that I'm taking the 0 and I'm plugging it in there for x. So what I have in this case, I'll put it off to the side because I want to not get in the way of what f of x really is, but it's 0 squared plus 1. This one's going to be 2 squared plus 1. This one's going to be 4 squared plus 1. Because I'm just plugging those numbers into the function. Well, we can do that in our head. 0 squared plus 1 is just 1. 2 squared plus 1 is 4 plus 1 is 5. And then 4 squared plus 1 is 16 plus 1 is 17. That's my heights. We called the width. So my area is 2 times 1 plus 2 times 5 plus 2 times 17. I'm just taking these numbers here and plugging them in. Well, that's going to be easy to calculate. 2 plus 10 plus 34. Well, 34 and 2 is 36, so it's 46. Now the problem is, that's the area of those rectangles. It's not actually the area that's under the curve because we see we missed some area. But that's our guess. That's not the total area, and probably be more accurate to say, hey, the area is approximately 46. That's the exact area of the rectangles, but it's the approximate area under the curve. And so you may be asking the question, well, why does it help if we don't have the total area? Well, the reason is, and again, we're going to see this a little bit later, if we've got this sort of a curve, we'll just look at the part that we have. Instead of 3 intervals, maybe we just have 6 intervals. So if we increase the intervals, 1, 2, 3, 4, 5, 6, so now maybe we have an interval that goes to 1. And then we have another one at 1. That's a little bit higher than the other one. And we have another one at 3. And we have another one at 4. We have another one at 5. Then we have another one. We don't have many other ones. We just go up to 5. So now what's going to happen, we're taking up more of that area. We're getting a better approximation. And so the basic idea here is the more rectangles, the better approximation. And again, you may say, well, that's great, but it's still an approximation. Well, I'll tell you what's going to end up happening. We're going to take the limit of these as that change in x, the width of the rectangles, approaches 0. So we're going to make those rectangles super, super thin. Think of a sheet of paper. If you have those all the width of a sheet of paper, you've got almost the exact area. Or if instead of looking at it as the width of x, we want to talk about it as we're taking the limit as the number of rectangles goes to infinity. Now I'm not going to write that down. We'll just leave it here for now because that's how we're going to build it. So it's the limit as x goes to 0. I haven't said of what, but it's of each of those rectangles. And I don't want to get caught up in the notation. It's using delta, and it's to add things up, but I don't want to add confusion there. I just want to say we're going to be doing this piece where we're taking the limit as those widths get smaller so the number of rectangles gets bigger. And once we take that limit, if it approaches a number, it actually approaches the exact area. And so we're going to do that. And if you remember where we went before when we were talking about derivatives, and we took the limit of the slopes of the tangent lines, and they became the instantaneous slope or the instantaneous rate of change at a single point. It's the same idea that we're going to do. Coming up. Okay, not yet, not today. What we're going to do is we're going to do one more example of these estimating the area under the curve using rectangles, just so you get a better feel for it. And then next section, we'll go on and we'll actually do it with calculus instead of just geometrically. Okay, let's look at another problem. This problem that we're going to do is actually problem 38. Let me get a spot to put it, and let me go jump in and grab problem 38 for you. So let's see, I have 38 right here. We'll go ahead and copy it. and paste it back in right about there. Okay, so now we've got another problem to look at. They actually gave us the picture here. So we can build from there. It says Rags Limited has found that its marginal cost in dollars for the X jacket produced is given by, and they give us C prime of X. Notice they're giving us the derivative. I'm going to even write that. Derivative. And they give us the picture, approximate the total cost of producing 400 jackets by computing. And I left out the notation because we don't need the notation. We'll just say by computing, and we're going to, and again, it's approximate the total cost by computing. I'm just going to say total area of the rectangles. So notice this time we're actually going to be an overestimate of what the total cost is, because notice all except for that bottom rectangle that has a lot of area above the curve. So if I just took the area under that C prime curve, that would be less area than what the rectangles are actually going to give us. So we're going to have a little bit of an overestimate this time, and that's okay because it's just an estimate. Okay, but let's talk about how we're going to find the area of those curves. So we've got 4 areas. So we have 4 rectangles, and they're each going to be, should I put equal? No, let's make that an arrow. It's not equal anything. So they're each going to be area equals length times width. Base times height, if you want to say that. I kind of like base times height, but we're usually used to hearing it as length times width. Okay, so let's do that. So I'm going to go area. We're going to say length times width plus length times width. I'm going to do 4 of these because we have 4 rectangles. Now the good part is the widths are always going to be the same. So remember in this case, I called that the length last time, didn't I? We'll still call them the length. The length of these are always going to be the same. So the length is total length, and again over the number of rectangles. And in this case, we go all the way to 400. Now, since I started at 0, if I was only going from, say, 100 to 400, then I'd have to do 400 minus 100 is 300 because the width would only be 300. But since we're going all the way to 0, it's the same as what the last one is, obviously. So divided by 4, so I get 100. So each length is going to be 100. So now when I do my area, we'll just call it A, I'm going to plug in 100 for each of those lengths. But let's talk about the width. And again, let's talk about this being the width. These are each going to be the length. It's not a very good L. There we go. So now we have to find this height right here. We'll notice that's from plugging 0 in, because that's what determines the height. It wasn't right here that determined the height of this rectangle. It wasn't here. It was up here that determined the height of this first rectangle. Well, that's C prime of 0. The second one, that's C prime of 100. The third one is C prime of 200. And the third height, or the fourth height rather, is C prime of 300. That 400 didn't determine the height because it's always from the left endpoint. And you could always do it from the right endpoint if you want, but in our book, they're always doing it from the left endpoint because we see in calculus, it doesn't matter which endpoint you get as long as you do that limit as the width goes to 0. You're going to end up with the same answer. So that's going to be what we're calling the width this time. So let's do that off to the side. So we'll do it down here so that I can plug back in up there. So I'm going to plug in my X value, and I'm going to plug in my, well, that was a little bit smaller than I had intended. And I'm going to plug it in and find out what C prime of X is. And remember, we already have, so I'm not going to write it down here, but C prime of X over in the original problem, I'm circling it. That's my formula for C prime of X. So I'm going to plug in 0, 100, 200, and 300 to get the various values of C prime. All right, here's what I know so far. Remember, my lengths were all 100. So it's going to be 100 times whatever my width comes out as, plus 100 times whatever my next width comes out. And I have that 4 times. If you want to, since those lengths are always the same, you can factor that out and write it as 100, and then in parentheses, just put the 4 widths, the first width plus the second width plus the third width. You could do it that way if you wanted to. I'm not going to write it that way because it doesn't look to me like length times width. But it's a shortcut, and especially if the hundreds were not such a nice number. But so you're welcome to do that. I choose not to. So I'm not going to. But let's find these. So I'm just plugging these into my calculator. With the 0, we know everything that doesn't have an x, that does have an x goes away. So the only thing that doesn't is that 50. But now I'm going to go in here and I'm going to go 0.0003 times 100 squared minus 0.2 times 100 plus 50. I get 33. Now, the good thing is it's less. We see that it should be less, and it looks like about 33 from the picture, so I have a good feeling that I plugged all of that in correctly. Now I'm just going into my calculator. I'm changing those 100s to 200s, and I get 22. Well, it looks about right. And at 300, am I going to get 11? Do I see a pattern? I get 17. Of course, I don't have a pattern. We would have had a pattern. It'd go down the same amount each time if it was a line. That's the definition of a linear function. It always increases or decreases at the same amount. So since I didn't have a line, obviously it's not going down as quick. And we see that because the derivative there is getting to be a smaller negative number. Okay, so we've got all those values. That was those heights, and we see that 17 looks about right. That'd be about here. That seems reasonable. So I'm just plugging those values in up here, these values. So my first rectangle, the length was 100, and the height was 50. My second one was 33. My third one was 22, and my fourth one was 17. So in my calculator, now I will tell you, I'm using that shortcut. I'm going 50 plus 33 plus 22 plus 17, and I'm going to multiply the whole thing by 100, and I get $12,200. That's my estimate of total cost of producing 400 jackets. We will find next time how to find that exact area. But right now, we don't know, so we're actually approximating it. And I'll give you a little heads up. There are some problems, especially in the new edition of the book, that talk about this, although we haven't seen this yet, and it's not very much in the old edition of the book. So this was my approximate total cost. If I wanted the actual total cost, what I do, and you may have thought of this, I'm going to take the antiderivative because they gave me the derivative, but I want the function, so I have to go backwards and anti-differentiate it. So I take the antiderivative of c prime of x dx, and I evaluate it starting at 0 and ending at 400. And that's going to give me the actual total cost. And I have the formula for c prime of x, but it doesn't matter at this point because we're not finding that. But we will see next section how to find that to get the actual total cost. But it's doing what we did last section where we anti-differentiate or take the integral. All right, so that's it for today. Hopefully that was helpful to you. We're zooming along this section really well. Make sure you stay up with the homework, and I will talk to you later. Have a great day, and we'll talk again soon.